think our ability to understand and to reason is a property of us. What category would that be? Oh. So my ability to know you is but my ability to know others is a power that's generic to all of us. So that's, in fact, you would say that's part of the human ability to know other people. But my knowledge of you in particular is an accident. It's a mere accident. It's not proper. So the word proper, what does the word proper mean? We use it a lot in conversation, but does anybody know what it really means?
With the social norm?
Yeah, that's not correct. That's what most people would say is it has to do with the social norm. What is proper? What's the proper definition for proper? What does it really mean? It means coming from the essence. Relating back to the essence. That's what proper means. So is it proper for me to be able to know other people? Yes, that's part of the essence of what we are. Our ability to understand and to reason is part of our essence. Distinguishes us from, say, a chameleon. Apparently has no ability to understand, think abstractly, or reason. Okay, but my ability to know, the fact that I know Mr. Patel, that's a mere accident. That specific thing does not come from my essence. To know him is not an essential accident. The fact that some of you were born in South Carolina, that's not proper. It has nothing to do with your essence. It's a mere accident. So I'm working my way to answer your question by talking about certain things. What are the proper powers of us? What are those things that are connected to our essence? Okay, and so thinking is part of that. Thinking is proper to us, part of our nature, part of our essence. Okay, and so we're talking with questions relating to, I think, has to do with the nature of our mind, and are they merely physical processes? I think that's what we're getting. Yeah, Mr. Nazir.
Would you separate, like in this sense, consciousness and intellect? Because like for humans, it would be very different from like a conscious other being or animal. That like,
yeah, I guess I have to know. I understand what intellect means. Intellect, properly defined, has to do with in us with our ability to understand and to reason, and that reason is a deductive kind of reason. We go from step A to step B and make conclusion about step C. So our deductive reasoning is part of our nature, ability to do that. In fact, that's how we think. Deductively. But consciousness, I'm not sure what you mean by conscious.
I guess
Is a chameleon conscious?
Yeah.
Okay. So I wouldn't. So that word I have to. I think is a lot of these things are ambiguous in common speech. People are very unclear about what they're talking about, and a large part of our job as scientists is to make these things more precise and clear, based on what we see, based on our understanding, observations. So, I guess your definition of consciousness would, I guess, so a kind of sensory alertness, response to sense.
I guess it kind of all just breaks down like to a very generic level. Because you're talking about consciousness, because like
okay, so
Chinese asking about
all sounds like all animals conscious? Is that
yes,
something?
yeah.
Okay, so I think what you're using consciousness is related to having senses.
Yeah.
To having the ability to sense and react to the senses. That's what you're calling consciousness, okay? That's not what everybody would call consciousness. So let's put sense nature instead of consciousness. Let's talk about sense nature. Are all animals, are all beings, living beings with sense powers? Are they all intellectual? And the answer is no. The alien is not intellectual. Does not have, apparently doesn't have the power that we do. You don't see comedians teaching class. Right? No, we even build buildings and we make special places dedicated to this one thing that we do, which is teach food. So these things, by the way, are all covered in the book, which if I had my druthers, all Clemson freshmen would read this book before anything else. Written by Dr. Rizzi, and it was the book that he wrote before he embarked on the task of writing these physics textbooks. You can get a paperback on Amazon, a new one, for about $20, I think. And there are copies in the library. Really good, really excellent, and it addresses exactly those kinds of questions. And it begins with the question of what do you really know, and how do you know it? That's an important thing to start with. And I think that I can tell you, you know a lot, it's just not what you think you know. Most of you think you know, for example, atoms. That atoms exist. We know atoms exist. And as I pointed out here before, you don't know about atoms. You don't have that kind of personal knowledge about the existence of atoms. You're relying on somebody who's told you. And what we're talking about, what you do know, you know the people in this room, and you know where you live, and you know the things out, you know air, and you know sun, and you know rain, and you know trees, you know things like that. In fact, those are the things you have a great certainty about. Much more so than Gaussians and probabilities and wave functions, atoms. So the important thing is that our understanding, to the extent we can be sure about science, like this stuff that we're talking about, is based on that other stuff. And that's what he's talking about. There's a science before modern science. It's the basic stuff the basic physics that we come to all have an understanding about the nature of physical things. So, and then he goes on to talk about intellect, difference between intellectual knowledge and sense knowledge. Remember that was at the beginning, we went over pretty quick. Sense knowledge is our knowledge through the senses of particulars. Intellectual knowledge is knowledge of things, universal aspects of things, different power. He goes on to investigate the nature of intellectual knowledge. And then goes back to the study of physical things and the essence of physical things. And how we are different than, say, a rock. Or a community. Yes, Mr. Rupp.
I just want you to know, I just checked the Zoom. Audio is good.
Yeah, audio is good. Thank you. Thank you. Okay, so let's suppose we have some kind of probability distribution, and you're working on a binomial probability distribution. Yes, ma'am.
Did the Zoom borderlines change?
Yeah,
Oh,
they did. I have to check them each time. Yeah, isn't that something? I have to recheck them. I know. There might be some way I could learn how to control the camera. There's probably maybe something over here. I'm not sure.
There's like a remote. My linear algebra professor does the uses like some sort of remote. I don't know which one.
Probably not this
It was
one.
a tiny. It was a tinier.
Tiny one. Okay. Maybe this. Possible. Okay, I'll play with that next time. All right. So thanks for that, because I want to make sure. So you're dealing with the binomial probability distribution, and you're going, which has to do, for example, with coin tosses, and turning that coin toss problem into a random walk, where you have set up an ensemble of walkers, they have some number of coins, each one, and they make a number of coin tosses, and that determines how they walk, and then you make a histogram of the result, the end, where they end up. Okay, so we have some kind of probability which represents the fraction of the ensemble that ends up at some position X relative to where it started after, say, 10 coin tosses, for example. And you know that this probability distribution for the coin toss problem has to end. That is, you can't go, if they're only in coins, you do have the possibility that all coins would be heads, but you don't have anything past that. Can't be anything. So there would be a finite range for this probability distribution. And so I'm going to assert, well, let's just leave this much. So we have, how do we make this? Well, we collect from the ensemble a set of, let's say the ensemble, there are M members of the ensemble. Big deal. So there are M such numbers. I ask everybody, where did you end up? Everybody tells me. And then we, based on that, we take a bin, we bin all of these observations and we put them into a histogram. And if I make a big ensemble, then I can make the bin sizes really small and I'll get a nice smooth curve, right? If I make an ensemble that has 100 million members, then, and they're all, say, doing 10 coin tosses, I'll get a nice smooth curve like this. Okay, so I might ask the question, what is the average over the ensemble of the final position? So I just add them all up and divide by the number. And for this particular distribution, like I just described, the random walks, what would the average be? Should be 0. Okay, but if my ensemble is big enough, right? It's possible if I have a small ensemble, it might not be 0. And so I could think of an ensemble of ensembles. Right? You can formulate such a thing. If I think about, I have 10 members in the ensemble, and then I could make, out of 100 people, I could make 10 ensembles of that. And then I would be studying variations within the ensemble of ensembles. Right? So there are layers of this that you can think of. So when I say it's an average here, I mean that I've made the ensemble really big, and there's some small chance if the ensemble is really big, it's not going to come out 0. The bigger I make the ensemble, the closer that's going to get to 0. There are going to be fewer and fewer ensembles which are not 0 for the average. Okay, and so in that case, we would expect, for example, in the random walk problem, that the probability distribution averages to 0, and so it's symmetric on both sides. The probability of ending up 5 steps that way is the same as probability for ending up 5 steps in this direction. So it's nice and symmetrical, and that would argue that the average should be 0. Okay. So the other thing of interest, other than the mean, this is average, also called mean, is the width of this distribution. So how do we calculate the width? Here's one way. I'm going to add up the squares of all those measurements and average those. This is the average of x squared. So notice the notation here, the angle brackets of something inside. We're going to be doing a lot of averages based on probabilities from the wave function. And so we're going to use this notation. So if I square it and then take the square root, this will now have dimension. Let me do it this way. Instead of putting it there. What is the dimensionality of this thing? It's the length squared, right? So if I change the system of units from, say, centimeters to inches, then it's going to change like a factor of 2.5 squared. Yes, ma'am.
Isn't that the spread?
Yeah, I mean, there are lots of terminology. We call it the mean. This is the mean squared deviation. There are lots of terms that you'll see relating to this. This is also called the first moment and the second moment. Yes, sir.
So for the mean square, is that, you're saying that's the average of the, from one side to the other?
Almost. Because it has length squared, we have to take the square root of this. So the root mean squared is the square root of this. And this corresponds to some measure of the width of this distribution. So it relates in some way to the width. It's clear that if I have a wider distribution, if I have another curve that looks like this, I'm comparing two different probability distributions. They're both symmetrical. They both have average 0. But this one will have a bigger width to it than this one, measured this way. Right? Does that make sense? Okay, so this is a measure of the width for a distribution whose mean is at about 0. And so we could go about doing it by just averaging the x's and the x squareds. And this would be one measure of the width of this distribution. Okay. Now you're going to show in your homework for the random walk problem. By random walk, I mean everybody has some number of coins, and then you do left or right depending on whether it's a head or a tail. Look at your in position, that the width was like the square root of the number steps, the number of coins in the toss that each person was made. I'm going to show this in your homework. Strange result. It's like diffusion. Remember when we talked about diffusion, if you take a colored dye and drop it into water and watch the blob, of course it's going to expand. The width of the blob will go like the square root of time. It's kind of strange because if you remember with impetus, you give something impetus and it moves along and the distance traveled is proportional to time. But here the distance traveled is proportional to the square root of time. Or distance traveled meaning the width of the blob. So like the square root. This is characteristic of diffusive behavior or a random walk. A random walk is kind of like a diffusion. And that's because as the molecules of the colored dye, as the colored dye is moving through the liquid, it's going backwards and forwards. And so there's a lot of missteps. Whereas the impetus carries something with intent, with a purpose in one direction. And so the displacement is linear. But if you add all of these kind of missteps, can't decide which way you want to go, then the width will increase with the square root of the number of steps. Yes.
Which, I know the height of that width.
Yeah. You mean the height, not the height of the width, but the height.
Oh,
Is that what you mean? This?
pardon me, Dr. You see how the width?
Oh, how do I know where to draw it?
Yes, sir.
Okay. Well, that's obviously, there's no unique prescription for that. And we'll define one here in a minute.
Because it could be, it varies.
Yeah, that's right. So one way to do it is to say, well, I get the inflection point. Another way would be to say, I want some fraction of the probability to be contained inside of that region. There are different definitions. So I'm just defining it this way. That's the definition.
But my confusion is because it's one set length. Right? If you have a set ensemble values, it's one set length.
If I have a probability distribution,
Yes, sir.
yeah, like one,
It'll be like approximately 5, for example. So determining the height, so you can't just draw only one of those widths is 5.
this does not correspond, this definition for the width does not correspond to a particular value for the height of this.
It does not.
Does not. All right. No. Different probability distributions can have the same width. Let me give you an example. Okay, so I have a probability distribution that's like this. It has 2 peaks. This is not the random walk. This is a different one. Probability distribution at minus A and plus A for X. Okay, probability of half here and a half here. So what is the mean? For this probability distribution, what is the mean?
0.
And what is the mean of X squared?
It'd be 1.
No. No.
It'd be 1/8.
No.
Wait, I'm sorry. A half.
Keep trying. No. A here has to involve A. It has to involve the distance from the origin.
Oh, it'd be 2A squared.
Not 2A squared. It's just A squared because each member of the ensemble either gets plus A or minus A. You square it, it's always A squared. So the average is going to be A squared over the ensemble. More formally, it's a half times minus A squared plus a half times A squared, right? So in other words, this is 1/2 minus A plus 1/2 A. That's the mean. That would be 0. This is 1/2 minus A squared plus 1/2 of A squared. A squared. Okay? So what's the width? A. For this distribution. But you can see there's no place to draw a line here. Don't get confused by sometimes the probability looks like a Gaussian and you draw a line there. It's not a smooth distribution. So I have this one. This could have the same width as, say, a Gaussian or a binomial distribution. Right? But this clearly, I don't have a curve that I can draw a line through. Saying I want 67% of the population inside of the mean, inside of this width. So how about another one? Let me draw another one. Here's another probability distribution. It's going to have the same mean and it's going to have the same width. Let's see here. I got to figure it out. I got to do this quick. So half of them are at 0. And then a quarter of them are at, let's call it minus B. And a quarter of them are at plus B. That's a different probability distribution. Yes, sir.
I'm sorry, Dr. Roth, but for the first one,
Yeah.
is the width not supposed to correspond to like between the two like peaks almost?
No, correct. This is a different measure of the width.
Okay.
This is a choice of measuring the width. You could have, say, make it 2A would be the width.
Okay, that's what I was like
Right.
thought. Okay.
Right. So this choice, the RMS, the root mean square deviation, gives you the width of this distribution, A, not 2A, but A. There are different choices for this, and they're not unique. This is the one that's very commonly used. like yellow chalk here. I guess we're gonna switch to yellow. No significance in the yellow. Okay, let's do this one. What's the mean of, what's the mean? 0, right? 1/4 at negative b plus a half at 0 plus a quarter at positive b. All ends up to 0. It's a nice symmetrical distribution. How about x squared? Okay, it's going to be 1/2 b squared. Right? You see how to get that? So if I choose b here to be square root of 2a, then I would get the same result as this would, right? So I have to move these out a little bit farther out than this one, and I put some of it in the center, changing the distribution, taking these two peaks. Some of them I'm going to push to the center, but I'm also going to push some of them out, and the result is the same width. So the width and the mean do not uniquely specify the probability. Lots of probability distributions with the same mean and same width. Okay. Throughout.
So it'd be more accurate just to say, like you said over here, like the width is approximate of A, or
I'm sorry, say that again.
would be more accurate, say like you did over here, the root of the square, that's like approximately the width. So when you just say like width is approximately A, or
No. This is the definition of the width. The RMS is the definition of the width that we're going to use from now on. Not approximate, defined. It's a measure of the width. It corresponds roughly to what you understand that something that has more extension out this way would be wider, but the exact value is just defined this way. This is our measure of the width.
so that squiggly means equal when you're doing.
Yeah, I take the squiggly away. It equals to what we're calling the width. The width is the RMS.
What about how it's also like equal to the square root of n? Would that be equal or would it be
Oh,
approximate?
that was a tilde.
Okay, so that would be approximate.
No, it's proportional to the square root of n.
You
Not
said
approximately proportional. I should have written
proportion.
for the random walk. I should have written width, meaning the RMS, is proportional to the square root of n. That's what I should have written. Yeah, thanks for fixing that. What I'm interested in the random walk is how does the width increase with the number of steps? I don't care about factors of 2 or pi or something you might throw in as a different way of measuring the width. Right? I just want to know how does it vary with the number of coins, number of steps. And this is the definition. The RMS is when I talk about width, the probability distribution, that's what I mean. No, so there are lots of, you could have different measures of the width. They're all going to be relating in the same way to A, right? It's going to be some other, maybe 2 widths, if you like. But this is the one that's commonly used. Okay. All right, here's another one. This one is a Gaussian, so you're going to have distributions that will come about from coin tosses, or say 10 coins or something like that. You get a probability distribution. Here's another one. It's a Gaussian, and the binomial distribution approaches a Gaussian as the number of coins in toss goes to infinity. So let's call it G because I'm going to be specific here. G of X is so there's a parameter in this thing called sigma. It's a exp of something is just the exponential. It's just a way of writing it because if I had to put all of this in the exponent e to the minus x squared over 2 sigma squared, it's just hard to write it because it's all got to be up in the superscript. Write it this way. Sigma's a parameter in the Gaussian. Okay. And to get the mean of x, I integrate over all possible values of x. This is the same as what I did here, except I have just certain discrete values. In general, if I have some probability distribution, the average is just the integral of x with that probability. So what do you think the mean is going to be? Yeah, nice and symmetrical. Just as much on the left as on the right. Okay, x squared. It is the integral of x squared multiplying the Gaussian. By the way, there's a table of integrals on Canvas that we will use a lot of. We're doing a lot of integrals in this chapter. There's a table of integrals, common integrals on Canvas. So you should download that. That will help you with your homework. Have all in one place. You should, by the way, have for yourself a place to go for getting integrals. Because you're going to do a lot of integrals over however many physics courses you're taking. You're going to do lots of integrals. Yes, ma'am.
On like a test in this class, are we gonna have to memorize those integrals?
Now I'll give you all
Thank
the
you.
integrals you need.
Thank you.
I'll give you more than what you need, so you'll have to figure out which one to use. All right, so this turns out to be sigma squared. And the RMS of the Gaussian is just sigma. And that corresponds to a point, I can't remember now. That corresponds to a point on here. X is plus or minus sigma. Corresponds to some fraction of the total population. I can't remember what the number is. Maybe somebody remembers.
Or something like 67.
Something like
Was
that.
like the empirical rule that the 50 stats.
Yeah, that's right.
Whatever E. Like one minus whatever E.
Something like that. I don't know.
It was a,
I don't remember. Let's see if he says here.
it was like 67, 95, and 99 within like 1 standard deviation, 2 standard deviation, and 3 standard deviation.
Okay, so give me one standard deviation. What's the population?
Like percentage wise?
Yeah.
Or something like 67.
Something like
I don't
67.
exactly remember what it was.
So this is also called a standard deviation. And by standard deviation, within one standard deviation of the mean, that is plus or minus sigma, 67%, something, some number like that, the number I can't remember, but it's the majority. Same fraction is within that distance from the mean for a Gaussian. Okay, so there's one parameter that describes a Gaussian like this. Just the sigma. It's also called, people typically call it sigma or standard deviation for Gaussian. Okay, to get any other value, I just do this integral. For example, I want the average of x to the 4th. I just multiply the Gaussian by x to the 4th, do the integral. It's going to be 3 sigma to the 4th, I think. Yeah, 3 sigma to the 4th. I just remember that. So notice, what's the dimensionality of sigma? It's a length. It's the width, right? It's related to the width, the standard deviation. So the exponential here, x is dimension length. Sigma has dimension length. The argument of this exponential is dimensionless, which it must be. Dimensional analysis of a transcendental function like this must be, the argument must be dimensionless. Otherwise, this thing changes in a complicated way if I change units from centimeters to inches. Notice there's a sigma down here. Remember, we said this is a probability density. How does the probability density, what is the dimensionality of a probability density? 1 over length. The other one that I didn't give here was that the total probability has to be 1 because it's a fraction. And so if I integrate the Gaussian over all possibilities, I should get 1. And you can see here that this is the length times the dimensionality of the Gaussian, and the Gaussian is inverse length. Then this will be dimensionless. You have a question, Mr. Rutland, or you're just raising your hand?
I'm sorry.
That's okay. Just making sure. You know, you might have gotten tired of raising your hand, because I'm just keeping on, so. Okay, well, we've been talking about functions that are symmetrical around the origin, but obviously a probability distribution doesn't have to be that. There are other possibilities. So in general, the mean for some probability distribution is not zero. So it's always true that the integral of the probability distribution of total to 1, the mean might not be zero. Okay, in which case this does not give us the width. If the mean is not zero, if this is not zero, then this is not the width. We have to do something else to construct the width. And that is the following. This is the distance from the mean. And we want to square that and integrate over the probability. We take the square root of this and we'll get the RMS. So let's go back and say that again. This tells us how far x is from the mean. Then I square that, multiply by the probability for being at x. Now this is the square of the width. So this is equal to the width squared, where the mean is not zero. You see the reasoning? Very similar to what we were doing before, but it's just where the mean has shifted. We could have a Gaussian that's not centered at the origin, for example, or probability distribution. It's not centered, not symmetrical, around zero. So the mean is not zero. So let's have a probability distribution that's like this. All right, it's easy to guess where the mean is for this. Yeah, so it's going to be right here for this. This looks like a Gaussian that's centered somewhere else. There's the mean. To get the width, I don't want to just do x squared, because that's the distance from the origin squared. I want to do the distance from the mean. So here's some value of x. So I want x minus mean, and then square that, and integrate that. So this is, in general, the measure of the width, not this. This works out, of course, if this is zero, if x, average of x is zero, then these two things are the same. But in general, this is the width. Okay, now we're going to simplify this. Let's expand what's inside that quadratic. And this is the square of the width, just expanding the quadratic. Okay, so now I can, I can distribute multiplication over addition here. The integral of a sum is the sum of the integrals, right? Because integral is all a bunch of sums. Okay, I skipped a couple of steps here. Can you see that I'm okay with what I did? So I have x squared times p of x. Well, that's this one. Well, first, is everybody okay with me distributing? Right, I have the integral of a sum. Now I've got three integrals. Everybody okay with that? Okay. Then the first one is the integral of x squared. That's the second moment. That's average of x squared. Now this one, I have 2 average of x times x. This is a constant. Right? We're integrating over different values of x. This is a constant. So I can pull it out of the integral. And then what is this integral? It's the average of x. Well, I get 2 times negative 2 times the square the average of x. And that last one, what is the integral of p of x? 1. Okay, isn't this fun? This is the width squared. Now this cancels out here, so this gives me this minus this. This is the square of the width. It's defined back here. See, understand the reasoning if I write it like this. But in terms of doing integrals, you just have to do these two integrals. These two, combine them in the right way, and you get the square of the width.
Oh, I'm just done when I realized I know what you did.
Okay, good. That's simple, isn't it? You take this, you take the second moment, subtract off the square of the first moment. This is the first moment. You could think of this as the zeroth moment. First and second. Take the second moment, subtract the square of the first moment. And that gives you then the square of the width. Yes, ma'am.
Why isn't that zero?
Oh, excuse me, hold on. Oh, okay. So, there we go. Makes all the difference in the world. Thank you. You see what the mistake I had? I said the average of x squared. I meant the square of the average of x. Should have given 0. Right? It's not 0.
It's not still the width squared.
Yes. Yes, ma'am. Now it is. Before it wasn't. Now it is. Thanks for catching me. Okay, so yes,
Do you
ma'am.
have a symbol you use for width squared, or do you just write width squared?
Do I have a symbol?
Or
Sometimes, well, for a Gaussian, it's just sigma squared, right? The width is just sigma, but no, no, I guess I don't have. Sometimes people will use sigma. Or generally, even though it's not a Gaussian distribution, you'll see sigma.
it's only supposed to be for a Gaussian.
No, I guess I could say maybe sigma would be okay to use for the meaning of width defined this way. Sigma of the distribution doesn't have to be Gaussian. So I guess I'm then corrected there. If there is a symbol that is most commonly used, maybe sigma would be it.
Did you start, is that actually how you derived that integral right there is from that?
From this.
Yes, sir. Is that how you obtain that integral?
Yeah, I squared, right? Right, the argument was I want to know how far is x from the mean, not how far is x from 0. So I don't square x, I square x minus x, the mean of x. Tells me how far I am from the mean, not how far I am from here. Because the probability, this probability distribution has a mean clearly not 0. So I want to take the distance from the mean and square that. And then I just, this is equal to this, right? Can you see that? I square this inside.
I'm sorry. Yeah, I plugged in. I just see the basic algebra. Yes, sir. I see the algebra. Yeah.
Yeah, from here to here is just square it, distribute the square. And then I break it down into 3 separate integrals. Okay. And then each one. Questions about that? This is very general. It's for any probability distribution.
Also, that's just well, the reason why we multiply x by p of x and integral is that you're just if you multiply x times the p of x, because p of x is just the density, right? The
Yeah.
probability density. You multiply it by the x, which is like I don't know how to say that, but that gives you the probability at that point.
P of x dx is the probability, it's the fraction of the population. So if I have from x to x plus dx, the width of this is dx, P of x dx is the fraction of the ensemble that fits in here.
Yes.
So it's like multiplying by the number of observations that are coming in there. normalized by the total.
What I was asking is, how do we get X times P of X, not dx?
Do this interval.
Yes, sir, I'm trying to understand why is X PX? Why is it X times PX? Why is X?
Okay, so I was going back, whenever I have a set of X's, ask everybody what you get. Hang on. Okay, so if I have a set of X's, what do? I add them up. Now, that becomes, for a continuous probability distribution, it just becomes an interval. This is the number of members of the ensemble that fall into that bin times the X for that bin. Can you see how these two things are the same? If I take my Xi, if I take, oops, excuse me here, just X. If I take my Xi's and I make a histogram, how many of them fall in this bin? And I'm just grouping members here into bins. How many have that? How many belong in that bin? That's P of X dx. Got it? So I could have a group here, like I could have, so I get suppose I have 100 million of these. How many of them were within 0.1 centimeters of 5 meters? So that I count how many. That's P of X, dx for 5 meters. And then I just multiply by the distance, 5 meters. Did that go by a little fast to go from here to an integral? Went by kind of quick. Okay, let me go back, and I have a couple of minutes. Let me do that again, just so everybody's got this. Okay, so I have a set ensemble, say 1 million. Each will give me their X. So I get 1 million of these. And I want to know the average. I do this. Add them all up and then divide by the number. That's good. Okay, everybody's there on that. Okay, but I have so many of them. It's kind of annoying to keep track of 1 million. If I can histogram it, bin it, then I can save myself some work. So I look here, among this set, I'm going to make a histogram. So how many of them have a value inside of this bin? Say bin number 1. So some number. And then I just multiply by the X for that bin times the number in that bin. And then I have another bin, which is next to it, bin number 2. Different number in this list, different number of them. I multiply for the X for that bin. So now I'm multiplying by fractions, by binning it. And then I just take the number. This is P for 1, P for 2, P for 3, P for 6, P for 7. And I multiply by the X for that bin and add them all. So I can take this, in other words, I sum over bins. And X for the bin times the probability for that bin, which is the fraction, the number of X's that have that bin value divided by the total. Are you okay here seeing this?
Is it because P bin, is it because P bin's equal to like some probability divided by X bin?
P bin is how many of these fall into the bin, into a particular bin. Right? They all, if I write out this list, I'm writing it by bin. number now. I'm writing out the values of X in this list and collecting them by bins, okay? So this number here is the bin number. Okay, now I regroup. This is bin 1. Okay, how many of them are in bin 1? I have to divide by n. 1 divided by n times the X value for that bin. Because they all have it in common. Now I need a second bin. And the third bin, the fourth bin, the fifth bin. This is the probability for bin 1. This is the probability for bin 2. Okay, so that's what this means. I can now, instead of adding up the individual values, I can bin them all. The members of the bin all have the same value of X. So then I just got to find out how many of them are in that bin, which is the number divided by the total fraction of the bin. That making sense? And now I could convert this to an integral. If X is considered to be continuous, then I can do that. The bin width there is dx.
And so P of X again tells you, when you make the histogram of those walkers, for example, tells you at that particular X value, that's how many of those,
That's the fraction.
at that particular point. Yeah, that's the thing I get confused at is why are we multiplying by X to that value?
Oh, because they all have different values of X. You're gonna add up the X's. And now you're just saying, how many X1s do I have? Divided by the total. I have 3% of them have the same X1. So that's the probability is 3%. And I multiply by X1. You're calculating the mean X. So you have to multiply by X. You have to multiply the fraction in that bin by the value of X for that bin. Anybody confused else? No, okay so far? It went by fast, and so I'm glad you're having me go back, because once you understand this is what you're doing, thinking about it in terms of polling and ensemble. But we're going to be doing these integrals over continuous probability distributions. And the content is the same. Right? This is just having a really large ensemble can be converted to a histogram, really small bits. Right? Get that idea? Having a really big ensemble means I can make my bins really small. So I can have a continuous function and do an integral over a continuous function. Okay. Same thing then for X squared. Right, want to multiply and have X1 squared. Right, how many times do we get that fraction in the first bin, but now we're going to multiply it by the square of X for that bin. And square of X for that bin, but it has the same fraction, same probability. So it gives this interval. Is that making sense? That's good. I'm glad you stopped because it goes by quick, and maybe I should have slowed down then. Okay. All right, so here's another distribution that you're going to look at. It's another Gaussian. Very much like the one I wrote down, except what?
X bar.
Yeah, X minus X bar. So where is this function peak? Where is the highest value of this function? Where the exponential, the argument of the exponential is 0. In other words, x bar. So this is a Gaussian shifted to have mean somewhere over here, x bar. So now the integral of this is still the same, still 1, which you can confirm by changing variables. X minus x bar, and it just you get x squared here instead of x minus x bar squared, and shift variables. The average of x is now, guess what, x bar, nice function. And the average of x squared, oh, this is complicated. It's not so easy. But if you take the width squared, this is going to be sigma squared. So this is going to be sigma squared plus x bar squared. Yeah, must be. There we go. So that this still gives you sigma squared. So this is a shifted Gaussian. And you measure the mean and the width in the same way as we just described. It's just a special case that occurs a lot in physics for good reasons. Actually, the reason for a Gaussian is very interesting. And maybe on Wednesday, if I remember, I'll tell you some things about Gauss. We'll find amusing. Okay, so I'll hang out here. Maybe other questions. But that's the end of class for today.